Hello everyone, welcome to the 40th lecture in the series. In this lecture we are going to solve the problem of merging patterns, and we are looking for optimal way of merging the patterns. So let me put this title in simpler terms. Imagine that we have two files, and the first file contains 10 records and the second file contains 5 records, and we are asked to merge those two files into one. So what we would naturally do is that we would copy the contents of second file and put them into first file, just because in the first file, as I said before, it contains 10 records, whereas the second file contains just 5 records. So it is easy for me to fetch those 5 records one after the other and add it to the first one, so that the 5 records from the second file would be appended to the first file. So if I do it otherwise, what I should do is that I should copy the contents of first file to the second file. In that case, I may have to access 10 records from file 1 and then I have to copy it to file 2. So what I have done with this, with the procedure of doing the or copying the second file's contents into the first file, is that I have reduced the number of data reads by 5. So the purpose of this topic is that we want to merge things into one. At the same time, we have to minimize the number of data reads that we make. And for finding the optimal way of merging the patterns or sequence or list, we are going to use the greedy approach. And with this introduction, let's move on to the lecture. So this is the problem of optimal merge pattern. So here we have sequences of different lengths, and we are asked to merge those sequences into one. At the same time, the constraint is we are supposed to minimize the number of reads that we make. Say for instance, if a sequence contains 5 elements and if I move those 5 elements to another sequence, then I am supposed to make 5 number of reads, right? And our objective here is to minimize the number of reads that we do on a sequence. So now we can replace the sequence with file or something. So any two sequences can be merged at a time. So this is also one of the constraints. We cannot think of merging more than 2 at a time. We can just proceed by merging 2 sequences at a time, and at every step what we do is that we merge 2 of the shortest sequences into one, and we will be keeping on doing this till we get the final output as a single sequence. Imagine that here with this example we have 5 number of lists, each with varying sizes. So for doing this, what we do is that we have sorted them according to their length or size, and as such L2 and L4 were the list with fewer number of elements, and so they have been merged first into one sequence, and this result is then merged with the next list with the minimal number of elements, and that was L5, and so we got this 25. 15 plus 10 is 25, and finally then we go ahead with the merging the list 3 to this result, and finally we end up with merging the list 1 with an element of 30 into the resultant sequence. So this is what we mean as the optimal merge pattern problem. So optimal merge pattern, it is a pattern that relates to merging of 2 or more sorted files into a single sorted file, and this type of merging is usually done by two-way merging method. As we saw before, we go ahead with merging 2 files at a time. If we have sorted files containing m and n number of records, then when we finally merge them into one, the total time that is required for bringing it into one file is order of m plus n. So the first file contains m number of records and second one has n, and so the resultant file will have order of m plus n. When more than 2 files are to be merged together, we are going to repeat the merging process in pairs till all the files get merged into a single file. So here we have an example. We have 4 number of lists, each with the varying number of elements, and we verify the same with the different permutations. So we try different ways of merging the lists into one. So let us consider pattern 1, where you could see that we have merged L1 and L2 first, followed by L3 and then L4, and if we do so, the total cost is will be like 11 plus 15 plus 17, which is 43. So this 43 actually corresponds to the number of data reads that we make while we merge the lists into one, right? And we consider another pattern where we merge L1 and L2 first and L3 and L4 separately, and together we merge the resultants into one, and here when you estimate the cost, it is going to be 34. So you could see that the if we revise the order in which we do this merging process, there is a change in the total cost, and of course it matters when we have more number of lists to be merged. And here we have another pattern where you could see that the lists are all sorted according to the number of elements they contain, and we have started from the lists with minimal number of elements. So L3 and L4 merged first, followed by merging of L2 with the result, followed by merging of L1 with the resultant, and when you do so, the cost has been estimated as 35. And when you observe the cost with the earlier cases, you could see that there is a difference, and here the reason why we study this particular topic is that given n number of files to be merged into one, our objective is to minimize the number of data reads that we may have to make, and we are going to use the greedy approach here. So with greedy approach, what we do is that we are going to sort the files according to their size, and we will be starting the merging process from the files with the least size. We go with merging 2 files at a time, and we will be repeating the process till we end up with one file. So if files x1, x2, x3 and x4 are to be merged, then there could be many different pairing methods. So this is one of the methods where we do x1 and x2 first, we merge them to get a resultant file as y1, and then we merge y1 and x3 to get another resultant file y2, and finally we merge x4 to y2, and this should be our desired merged file. And there is one another way of doing this merging. We merge x1 and x2 to get file 1, x3 and x4 to get file 2, and finally we merge y1 and y2 to get the desired file or the merged single file, right? And the different pairings usually demand different amounts of computing time, as we saw with the previous example. So in this example, what we have considered is that we have taken 3 files with varying lengths. So first file contains 30 records, second one contains 20, and the third one contains 10 records, and we are analyzing the same. What if we merge the first 2 files in one go to get the resultant file y1? So just because the first file contains 30 and the second one contains 20, when I merge them to another file y1, then I may have to move 50 records, 30 from first and 20 from the second. When I merge the resultant y1 with x3, then I will be getting the desired sorted file, and desired sorted file will have, it will have 50 plus 10. So I may have to compare these 10 records with the 50 records in the merged file, and altogether that will cost me 60 moves. So when I measure the total moves, it is going to be 110. On the other hand, when I consider this way of operation, like merging x2 and x3 to get the file 1, so x2 and x3 is 20 and 10, which is 30, and merging y1 with x1 to get the desired sorted file, it is 30 plus 30, which is 60. When I estimate the total record moves, it is going to be 90. You know very well 90 is less than 110. So here, that is the reason why we are interested in bringing this access time, reducing the number of moves that we make when we sort the files and make them one. And here we make a greedy attempt to obtain the optimal merge pattern, and at every stage in this approach we think of merging 2 files at a time. Let us see an example to understand what this optimal merge pattern is. So in this example, we are considering 10 files, each containing different number of records, and as you see here, 28, 32, 12, all of these are number of records those files contain. Now we look at optimally merging these two files together to make it a single file. So first we start with merging the smallest of the files. By smallest I mean the file containing a minimal number of records. So first we merge files x9 and x4 into one to get the resultant file z1. So x9 contains 3 records and x4 contains 5 records, and so 3 plus 5 is 8, and so we say that it involves 8 number of moves. So we have constructed this binary tree. So we use a binary tree here just because we take 2 files at a time. So 3 and 5, that has resulted in a new root which is 8 here. And then we merge file 10 with the resultant. So the number of records in file 10 is 11. So 11 plus 8 is 19, and so we have created a new root in this binary tree, and the resultant as well as the file x10 has become its children. So likewise we have merged 2 files at a time, and that is how we have constructed this binary tree. And this binary tree just depicts the merge pattern we have adopted to make all these file into one single file, which is z9. So altogether, to construct this z9, we have made this number of moves. That is what we have summed up and listed. So the total number of moves that we have made to merge all these 10 files into one single file is 1042. And of course, just because we have adopted this greedy approach, it is minimal. Otherwise it would have been it would have costed us even more number of moves to make it a single file. So here we have one more example where I have given I have considered 5 number of files with different number of records. So here you could see that we have started merging from the file with minimal number of records. In our case it is x3 and x4. We have merged them to make z1 as one file, and then what we have done is that we have taken this resultant and another file, that is z2 with minimal records by that time, and we have merged them to make another temporary file z2. Likewise we have repeated this process, and finally it has resulted in one file z4, and the total number of moves that we have made is 205. We have just summed up to get this value. And as you observe this binary tree that represents the merge pattern, you could see that we have some nodes as leaf nodes and some of them are internal nodes, and leaf nodes are all denoted by squares and internal nodes are shown with oval, right? And here each internal node has exactly 2 children, and it represents the file obtained by merging the files represented by its 2 children. So I was telling you that we constructed that binary tree by merging 2 files into one, and the number of moves that we made in total was actually represented by some internal node, and we call them as a root by at that particular point of time. So that is what we say, every internal node has exactly 2 children, and it was obtained by merging of files that were represented by its children. And the number in each node is the length of the file, and the external node, for instance, if we consider node x4, it is at a distance of 3 from the root node, which is z4. So in this example, this is our x4. So when you analyze the distance of x4 from the root, it actually, the path contains 3 edges, and so we say that it is at a distance of 3. Hence the records of file x4 will be moved 3 times, once to get z1 and once again to get z2 and finally to get z4. So what we say here is that just because x4 is a leaf node, every time I construct z1, z2 or other nodes that are all higher in the hierarchy, so for all of these ancestors, this x4 has to be disturbed. So we may have to read or access x4 while we constructed z1, and then while constructing z2 also this x4 has to be accessed, or data read has to happen with x4 and similarly with Z4 also it happens. So what this distance actually conveys is that distance actually tells the number of data movements that happen to a particular file, and hence the records in the file x4 will be moved 3 times for computing each of this z1, z2 and z4. If in case if we denote di as the distance from the root to any external node for particular file xi, and qi is the length of the particular file xi, then the total number of record moves for this binary merge tree is given by summation over I equal to 1 to n di into qi, where qi denotes the length of the particular file and di is its distance from the root, and this sum we call it as weighted external path length of the tree. So with this one particular weighted external path length, we may be knowing the number of moves that we actually make while merging all these files into one single file. So now let's see the approach that we have used with the optimal merge pattern. Let us consider that we have n number of sequences that are to be merged. So we can say them as sequences, or we can even use the term files here, and we are using the greedy approach. With the greedy approach, we select the minimum length sequences, let them be Si and Sj. Then we compute, or we create a new set S dash, and that S dash is S minus Si and Sj. That is, we have removed the elements, I mean the files containing the least number of records, and S dash is equivalent to S minus Si comma Sj union of Si plus Sj, because now it becomes a separate tree, and we keep on repeating this procedure until only one sequence or only one file is left. And when we look at the implementation aspects, we can make use of the heap data structure. The kind of heap is a minimal heap or min heap. So you know, in a min heap always we can find the minimal element in the root, and in a min heap always the parent node will be smaller than its children. The value held in the parent will be smaller than the children. So the root of the min heap will always contain the minimum element from among the set of elements available in the heap. So always when you do a deletion operation on a min heap, that will help you to retrieve the minimal element in a constant amount of time, and whenever you want to insert a new element onto a heap, insertion will take a time of order of log n. So deletion takes a constant time which is order of 1, insertion will take a time of order of log n. And this is the algorithm that we follow for optimally merging patterns into one. We start with the list, then we sort all the files in the increasing order of their length, then we begin merging 2 files at a time, and the 2 files that we take into consideration should be the one with least number of records, and we merge them and replace with one resultant file, and we keep on repeating the steps till we end up with only one file at the end. And for implementing the same, as you know, we saw that the optimal merge pattern resulted in a binary tree. So we see this algorithm. What we do is that we have a loop that runs from 1 to n minus 1. So this algorithm should help us to get one binary tree, and the root of the binary tree denotes the file that contains records being merged from all the other files, and this loop runs for n number of times. So what we do is that we make a call to a function get node of t. So get node of t will help us to create a new node, and then the left child of t is given value of least of L, where least of L is a function that would help you to find the file containing the least number of records. So we fetch one of those files containing the least number of records and make it as the left child of the tree, and we make a call to the least of function at another time, and the next file containing the least number of records would be made as the right child for the particular node t, and then we need to compute the sum of records on those two files, and for that we use the weight of function, weight of L child of t, and weight of or child of t, we compute, and that will help you to know the number of records on each of those files, and finally we sum it up and we put that as weight of the particular node t. So and then what we do is that we insert this new node onto the binary tree that we have. So that is insert of L and T. So we will be repeating this process n number of times till we end up with one binary tree, and that binary tree, I mean the root of it, contains records from all the files that are to be merged. So as such, the algorithm has a list of trees as input. So initially we consider all of those files, individual files, as one node tree, and so we say that it contains L number of trees, and each node in the tree will have three fields, one for L child, one for I child, and another for weight. And initially the tree in L has exactly only one node, and this node is an external node and has left child as well as right child fields, and why weight is the length of the one file that is to be merged. And we had the function named getNode of t that provides a new node for use in building the tree, and we made use of a function called least of L. As I told you, it helps you to find the tree from among the set of trees in L with the least number of records, and I told you the purpose of the function named weight. And insert of L comma t will help you to insert a new node onto the tree. And as such, in that algorithm we noticed we had a loop that runs n minus 1 times, and if L is kept in non-decreasing order, that is, we have to take the files in increasing order of their order of the number of records in it, and so that is what we mean as kept in non-decreasing order according to their value in the roots. And then least of L requires order of 1 time, and insert requires order of n time, and so we say that the total time required is order of n square. If in case we make use of min heap for its implementation, then as I said, min heap always contains the minimal element on its root, so deletion would take you order of 1 time, and insertion would take you order of n time, and so we say that the total time is order of n into log n. So we see one more solved example here. So here we have a sequence, and we are supposed to find the optimal merge pattern. As you know, we have to sort this data first in increasing order of length, and then we can begin merging them two at a time to get this binary tree. And when you are asked to compute the total time for merging this data into one, it should be the values available in internal nodes, and we have to take it and sum it up to get the final value. So this 216 is the total number of reads that we may have to do to merge these sequences into one single sequence. So to summarize what we have seen so far, the problem we have taken into account is we have n number of sequences of different lengths, and we wanted to merge all those sequences or files into one single file, and the goal we had is that we want to minimize the number of data reads that we make while we merging them into one, and we wanted to minimize the total number of data reads that we make. And for solving this particular problem, we made use of the greedy strategy. With greedy strategy, what we did was we took only two smallest files at any point of time and merged them into one, and we repeated this process till we get only one file as the resultant. And at any step, at the final stage, we even computed the cost, and for computing the final cost, we use the cost of merging the subfiles into one, and the cost of merging two files is the sum of their sizes, and we had several locally optimal sizes, and finally that locally optimal solutions were used to compute the total cost, which is the sum of all individual merge costs. And for implementation sake, it is better that we use a min heap or the priority queue, and we know the running time for that algorithm would then become order of n into log n due to repeated insertions and extractions. In real world, this particular problem can be extended to Huffman coding, that is mainly used for data compression, and for external sorting purposes, and scenarios where where there is a need to combine sorted data into one file. So in those situations we can very well use the same concept of optimal merge pattern. Now let's look at some of the review questions to test our understanding of the concept. First is, what is the main objective of optimal merge pattern problem? So here our objective is to merge several files into one single file, but while merging we need to minimize the total number of data accesses or reads that we make. And why does the greedy approach always merge the two smallest files first? We know that we want to minimize the access time, so the files that were merged first would be naturally at the leaf level in the binary tree, and we know very well that as we go up the tree, the files at the leaf level would also account for the data accesses that have to be made while combining them together. And that is why we use in the greedy approach we adopt this concept of merging two of the smallest files at any point of time, just because as we go up in the hierarchy their contribution would be less when we estimate the access time or the number of data reads that we make. And what data structure is commonly used to implement the optimal merge pattern efficiently? So we have learned several data structures by this time, of which min heap would be the best, because at any point of time we want only the minimal element to be returned as the result. So we want to look for files with minimal number of records. So delete min naturally has the minimal element on its root, so it is sufficient that we make a deletion operation every time to get the minimal element. And this deletion operation can be done at a cost of order of 1 in a min heap. And once this new node is constructed, it has to be added up to the tree again, and insertion can also be done on a heap in order of log n time. And so that is the preferred data structure for implementing this optimal merge pattern. In the optimal merge pattern, what is the cost of merging two files and how is the total merge cost calculated? We take two smallest files at a time, and for every file we have certain records with it, and the cost of merging those two files should be the sum of the records on those two files. And in order to estimate the total merge cost, what we do is that we take into account the sum of cost at all the internal nodes. We sum the cost available at all of those internal nodes in the binary tree to estimate the total merge cost. So I hope you are thorough with this as we learned this with an example. So thank you for watching.